Okay, I have the pleasure to introduce our guest, Francesco Mele. He's here today and tomorrow, so feel free to chat if you have time. Francesco is a great expert in the context of quantum learning, tomography, especially with continuous variable systems. He is currently PhD student in Scuola Normale in Pisa, and is going to join the group of Francesco in Caltech. So please, the stage is yours.
Thank you very much for the introduction. It's a pleasure to be here. Yes, I'm very happy to. Today I'll talk about some recent works about the topic of quantum learning theory with continuous variable systems. And it has been made in collaboration with a great team of people that are listed here. And so first, let me briefly say what are continuous variable systems. They are, roughly speaking, quantum optical systems. And maybe in quantum information, we are more used to the concept of one qubit or one qubit. In continuous variable systems, the concept of one qubit is replaced by the concept of one mode. So basically, you can think about one mode of continuous variable system as one qubit with infinite dimension. So it's basically the span of all the so-called clock states, ket 0, ket 1, and so on for all the natural number. And this is the Hilbert space of one mode of continuous variable system. So it's basically one qubit with d equal to infinite. And by definition, a continuous variable system is a system that consists of n modes. So n qubits with d equal to infinite. Now, okay, let me briefly tell you what is quantum learning theory. So quantum learning theory, it's another important branch of quantum information theory that studies how to efficiently learn properties of quantum systems as efficiently as possible. And so quantum learning theory has been extensively developed for 5-dimensional systems, and fewer analyses are available in the continuous variable setting. And continuous variable systems are infinite dimensional systems. So studying the intersection between quantum learning theory and continuous variable systems is a promising ground for new research. A lot of open questions are available. And quantum learning theory studies problems in the framework of the so-called sample complexity guarantees. So, there are many promising natural questions in this area, like questions like quantum state tomography, so learning unknown states of continuous variable systems, or quantum process tomography, learning unknown channels, or property testing, like understand whether an unknown state is, for example, Gaussian or not Gaussian, or understanding whether an unknown state satisfy a property or not, and so on. And one wants to do it with rigorous guarantees on the error that you are making on your task. Let me start.
Just a minute.
Yes.
Your slide is still stuck. The first slide.
Okay.
Do something with this one.
Mm-hmm.
Yeah, no, it's fine.
It's fine.
Move to the next one.
Is it okay?
No, it's still stuck.
Hmm.
Can you go to the next one?
Like this? Okay, if I do this, it's okay. So you don't have to do full screen, I guess. If I do. Okay, so let me start from the most basic problem of quantum learning theory, that is the task of tomography. So tomography means basically learning an unknown quantum state. The task is that you have many copies of your unknown density matrix rho, and the task of tomography is to take in input these n copies, apply a quantum algorithm that produces an estimator rho tilde that is an approximation of the true unknown state rho. And the requirement that we want in mathematical terms is that basically rho tilde estimator is close to rho in trace distance with high probability. So people use the trace distance because it has a strong operational meaning in terms of so-called Ohn-Weierstrom theorem. The task of tomography depends precisely on the measure of error on which we want to the error guarantee on our state. And the people use trace distance because as a physical interpretation. And the requirement is that the output of the tomography algorithm is epsilon close to rho with large probability, with probability close to 1. And the tomography algorithm usually has a promise. For example, that the unknown state is promised to be a subset of set of quantum states. For example, let's say the set of, for example, Gaussian states. Or the problem change with respect to this set S. Okay, so by summarizing, the problem of quantum state tomography is as follows. Given n copies of the unknown state rho, the goal is to output a classical description of an estimator rho tilde, such that it is epsilon close to rho in trace distance with high probability. And so basically, okay, here it's like for any unknown state, like there is no ensemble. It's like a worst case requirement here. So it's like the state rho is promised to be in this set S, and it is fixed, and we want to learn it with precision epsilon with high probability, where the probability is taken in with respect to the outcome rho tilde. And the definition of sample complexity is the minimum number of copies of rho that allows you to achieve these guarantees. So the minimum is taken over all the possible tomography algorithms so that allows you to get these guarantees. And of course, one can modify this definition and say okay, I want to restrict just to some specific tomography algorithm, for example, the ones that exploit, let's say, single copy measurements or just, for example, Gaussian measurements. This defines new notions of sample complexity, and it's interesting to study all these notions of sample complexity. But the first problem that one asks is what is the sample complexity, the minimum number of copies among all quantum algorithms, all tomography algorithms with no restriction, just the ones that are allowed by quantum mechanics. And so let's see some examples. For example, for tomography of qubit states, if your unknown states are mixed qubit states, the sample complexity is known to be d squared over epsilon squared. If the prior set is the set of pure states, qubit pure states, the sample complexity reduces to d over epsilon squared. Okay, so for example, for an n qubit states. D is 2 to the power of n, and so the sample complexity, as expected, is grows exponentially in the number of qubits. So we would like to do another thing also for continuous variable systems to study the sample complexity of tomography as a function of the number of modes. So, okay, but recall that here we instead of 1 qubit we have 1 mode, that is 1 qubit with d equal to infinite. So it's simple to realize that if we want to learn a state of continuous variable system with no assumption, the sample complexity is infinite. This is because the dimension is infinite, so the formula for the sample complexity of the 5-dimensional setting directly implies that you cannot achieve tomography with no assumption on the state. But the question becomes meaningful if you put some prior assumption on the state. And one very physical assumption is to assume that the state has a bounded mean energy. So basically, in laboratory, states have finite energy. For example, you know that your quantum state of light in your lab has a mean energy that is bounded by the state, the energy that the energy budget that you have in the laboratory, of the energy of the power of your light source, let's say. So you have the promise on the energy of the unknown state. So one can define the energy observable, the total photon number, that is acts on the Fock basis in this way. And the restriction that we have, the assumption is that the unknown state rho satisfies that the mean value of the energy operator is bounded by some known constant. This known constant is the energy budget in the laboratory. And the energy is an extensive quantity usually. It typically scales with the number of, or in the number of modes. If you have the energy in physics is an extensive quantity. Since we are interested in the scaling with the number of modes, we redefine this E top with a parameter n, just to avoid the implicit dependence on the number of modes. This is just a definition. Now E represents the energy per mode, basically. And okay, so basically, the first question that we analyze is that what is the sample complexity of learning the states with energy, with bounded energy by E? Now we have the problem makes sense. The sample complexity is not infinite, and the intuitive result is that if you require an energy constraint like this, you have the tails of your the state is still infinite dimensional, but the tails of your probability distributions are suppressed when you achieve a higher Fock number. But still, it's not a finite-dimensional state. And okay, the sample complexity is given by this formula. Basically, it grows exponentially with n, and has also a power epsilon to the power of 2n here, the resistance error. This is different from a finite-dimensional setting because in finite-dimensional setting there is epsilon squared. Here there is epsilon to the power of 2n. This is why we say that tomography of continuous variable systems is extremely efficient because this is a very favorable scaling. While in qubit, for qubit you have the 1 over epsilon squared, here we have the 1 over epsilon to the power of 2n. So that if you want to decrease the error by a factor of 2, here you have to pay exponential factor, while for qubit you have just to increase your number of copies by a factor 4. And just to see a fun example, if one want to perform tomography, let's compare tomography of qubit with tomography of continuous variable systems. If you want to perform tomography of 10 qubit state with resistance error 0.1, and let's say that you have one copy each 1 nanosecond, the total time required by the best tomography per qubit is just 0.1 millisecond. However, if you use the formula for tomography of continuous variable systems and you make a fair comparison by considering 10 mode states with energy per mode 1, so this is like the analogous of 1 qubit, because of the one photon, at most 1 photon per mode, it comes out that the total time is 3,000 years. That's so there is like a separation, a huge separation. So, and this is really due to this scaling epsilon to the power of 1. Okay.
Can I ask you
Yes, sure.
a question? Does the scaling change if you assume energy to be equal to something instead of less than? Like, I wonder, is this scaling due to like achieved by the states that subway is bound, or doesn't really make a difference if there is an easy answer to that?
That's a good question.
Like, it would make sense that the most energetic states are the hardest to estimate. So I wonder maybe the bound actually is for states equal to rather than the lowest.
Okay, we use also the states that have energy less than.
So it's easier to estimate states that have a fixed energy. I mean, then you can argue it's a less similar assumption.
For sure it's easier. I don't know how easier, but I think that I can answer this question later if I think. I still have to think a bit about it. But I think it's really doable to answer it quickly. Okay. So by summarizing, we saw that learning arbitrary energy constraint states is highly inefficient. But it's also true for a lot of practical scenarios. In quantum optics, we have the assumption that the state is a Gaussian. And Gaussian states are ubiquitous in both in nature and in laboratories. And they are basically the quantum generalization of the Gaussian probability distributions. Okay, now I'm not entering down the details of the definition of Gaussian states. I want just to give you a rough intuition of what Gaussian states are. So in physics, one can define the position operator and the momentum operator of each mode. These are in terms of the integration operator. And one can define basically the quadrature operator vector by putting the position momentum operator in a vector. And basically, in physics, quadratic Newtonians in the integration operator or in the position momentum operator are ubiquitous. And also Gibbs states associated with Newtonians are very important. And the definition of Gaussian states is precisely the Gibbs states of quadratic Newtonians in the quadrature, in the position momentum operators. So equivalently, Gibbs states of quadratic Newtonian in inertial and creation operators. These are Gaussian states. And okay, we will not need this definition. We will just need the fact that Gaussian states are uniquely identified by the first moment and by the covariance matrix. First moment and covariance matrix are basically can be written in terms of expectation values of the position momentum operators, and the covariance matrix is like a quantum generalization of the concept of classical covariance matrix of a probability distribution. And as in classical probability theory, a Gaussian state is uniquely identified by the first moment and the covariance matrix. And also, these quantities are expressed as expectation values of positional momentum, that they are observable. One can measure these quantities in lab via homodyne, heterodyne detection. So basically, This can be estimated in a lab via split procedure. So since these covariance matrices first moment uniquely identify the state, one easily identified tomography algorithm for Gaussian state learning, because just measure the first moment covariance matrix, and then since there is a one-to-one correspondence, you have estimated your unknown Gaussian state. However, this is not so simple, because we want to have guarantees with respect to the phase distance on the state. So basically, the question is, if we estimate the first moment covariance matrix of an unknown state with precision epsilon, let's say in some norm, for example, 2 norms, Hamilton's norm, what is the resulting trace distance error on the state? We would like to find the bounds, for example, let's say that rho D is a Gaussian state with covariance matrix D, 0 first moment for simplicity. We would like to find a bound of this form that the trace distance between 2 Gaussian states with covariance matrix D and covariance matrix W is upper bounded by some notion of norm between V and W. This is so because we need that to do sample complexity analysis. We want to estimate the covariance matrix. So W, for example, you can think about the estimator of V, and from that to propagate the error from the covariance matrix estimation to the trace distance. And it turns out that finding these bounds is very difficult. We found one first bound in our first paper, but it was not tight. Then Alexandro Lego posted a paper where improved this inequality, but it was still not known to be tight. And also there were follow-up works. And at the end, in our work, we find the tight inequality of the trace distance between 2 Gaussian states in terms of distance between covariance matrix. And tight inequality looks like that. I mean, it's tight in the sense that this coefficient cannot be improved, and there exist states that separates this in the scaling with these parameters. And okay, so basically, if you estimate your covariance matrix up to precision epsilon in operator norm, you are estimating your Gaussian states up to epsilon precision in trace distance. And okay, one can prove actually a more general inequality of this form. And okay, so by using these inequalities at hand, one can quickly do a sample complexity analysis of the tomography, for example, doing heterodyne detection or homodyne detection. And one obtains basically sample complexity that is polynomial in the number of modes and polynomial in the energy. And so basically, the sample complexity is polynomial, and so we say that tomography of Gaussian states is efficient. It's not anymore exponential in the number of modes, but polynomial, so they are not much more efficient to learn. And okay, so this sample complexity is achieved by protocols that are very simple, that are like heterodyne or homodyne, that allow you to estimate your covariance matrices. And achieve this scaling here. Okay, actually, in the follow-up works that we are posting in a few weeks, we actually improving the sample complexity of under heterodyne tomography. But yeah, this is a detail. What it's more important is that is this energy dependence needed? Actually, it's not needed. We show that there exists another tomography algorithm for Gaussian states that achieve a nearly independent, energy-independent sample complexity, and a sample complexity that depends on the energy just with up to log E factors, that is very small. A joke is that if the energy is the energy of the universe, log energy is tiny. So basically, it's a very we call this algorithm Gaussian energy-independent tomography algorithm for this reason. And the sample complexity is this one. And this algorithm is not the trivial one of estimating the covariance matrix and then propagate the error, but is a bit more involved. Basically, is okay. The idea of this tomography algorithm is to do the first round heterodynamic interaction and to estimate the covariance matrix roughly. Then writing the covariance matrix in Williamson decomposition to understand the direction of the squeezing, and then adaptively do this apply this Gaussian unitary with reverse symplectic in order to unsqueeze the states. And you do this operation a few times in order, for example, this is the initial unknown state. And at the first step, you do heterodynamic tomography. Then you understand a bit what is the squeezing. Then at the next step, you do, let's say, what's called general dyne with respect to this active direction, and so on. So basically, at each step, you adaptively choose a new Gaussian measurement to perform, and this is much more efficient than heterodynamic tomography. And it uses just a protocol that is experimentally feasible because it uses just a squeeze state, passive Gaussian unitary, and homodynamic interaction. But it's adaptive, so you don't do the same operation on each copy, but you adapt the measurement that you do copy by after copy. It's an adaptive protocol. And actually, we show that in a flow-up work, we show that adaptivity is necessary to achieve optimal sample complexity. Otherwise, polynomial energy dependence is actually needed. Here, I really don't want to enter into detail from the algorithm. It's just what I told you before. So basically, you do log iteration, and at each step you do heterodynamic tomography. You write then the Williamson decomposition, and then at the next step you apply back to the unitary basically squeezing the unitary that you have learned roughly, and you do this operation log e times. At the end, you have an improved sample complexity, and the sample complexity is just log e. So can one do better than this protocol? Or is this protocol optimal? Now, this is an ongoing work. It will, it's finished. It will be online in a few, I think, in 2 weeks. And actually, we show that this protocol is optimal under Gaussian protocols. I mean, if you restrict just to Gaussian protocols, so protocols that employ just Gaussian operations, possibly with adaptivity. So Gaussian unitaries and Scylla that are Gaussian, reading outcomes and then conditioning on the outcome and so on. Then we show that any tomography algorithm that uses only Gaussian operations actually needs at least n cube over epsilon squared. So actually, the sample complexity, this sample complexity is tight under Gaussian protocols. One cannot do better. So this is the optimal algorithm. Let's say up to log e, it's the optimal algorithm. And this lower bound applies even if the states are not squeezed. So if the unknown state is so-called passive states. Passive states are basically Gaussian states that can be prepared by applying to thermal states just being split at phase space rotation. So basically, Gaussian unit that does not increase the energy. And I'm telling you this detail because actually we show that there exists a protocol that learns passive Gaussian states with less sample complexity, with a sample complexity of n squared. So there is and this it's achieved by a non-Gaussian protocol. So basically, the non-Gaussian operations allows you to learn better Gaussian states than Gaussian operations. So while any Gaussian protocol has a sample complexity that scales at least with n cubed, there exists a non-Gaussian protocol that learns it with fewer number of copies, with n squared. And later I'll tell you what is the technique, what is this non-Gaussian protocol. And then, okay, actually we proved that if you have the further restriction that the states is a pure Gaussian state, this is the optimal sample complexity. And this is achieved via a Gaussian protocol. That is actually this energy independent protocol with a better post-processing analysis designed to tailor to pure state. And so the sample complexity of pure state, pure Gaussian state tomography is n squared over epsilon squared. Okay, and then we show also a lower bound on the sample complexity of tomography of Gaussian states under arbitrary protocols. So while this result was under Gaussian protocols, this is under any quantum protocol. And actually the lower bound that we prove is n squared, while under Gaussian protocol is n cubed, here it's n squared. And it is an open question whether this lower bound can be actually achieved via a non-Gaussian protocol. For passive states, yes, it would prove it. For non-passive states, it's not still known, but we will have follow-up work on that. And so basically, we have a sort of non-Gaussian advantage in learning passive Gaussian states. Basically, in the task of, basically we have a separation between Gaussian and non-Gaussian algorithms for tomography of passive Gaussian states. So basically, by summarizing, there exists a non-Gaussian tomography algorithm that solves this task with n squared number of copies, while any tomography algorithm that uses only Gaussian operations requires at least n cube copies. In particular, non-Gaussian algorithms provide a strict polynomial advantage over Gaussian algorithms for tomography of passive Gaussian states. Okay, now I'll tell you what is this non-Gaussian protocol. This is a really recent and cool technique that it has been introduced by Tang, Wright, and Zandri, and it's known as random purification channel. The random purification channel, it's a channel that allows you to take input copies of mixed states and convert them into copies of a fixed yet random purification of the state. So in quantum information courses, we learn about purifications of mixed states as merely mathematical objects with no physical interpretation, with no physical way to prepare a purification of the state given your mixed states. And this is actually true. I mean, there are number theorems that shows simple number results that allows you to tell that if you have one copy of your mixed state, you cannot convert it into a purification via quantum algorithm, agnostic to the mixed state. However, if you add the randomness into play, you can actually produce random purifications, meaning that there exists a quantum channel, lambda purified, that takes in input any arbitrary row tensor n with row list, and outputs a convex combination of n purifications. So psi rho is the standard purification associated with rho, And this result tells you that you can convert n copies of a state into n copies of a random purification. So this new technique has been used in the last few months across all the quantum learning theory to convert the proofs that proofs that were some results that were extremely difficult to prove. Now with this new tool, the random purification channel becomes like one-line proofs. And so basically, we have a physical process that takes in input n copies of your mixed state and produces n copies of a fixed random purification. Okay, why?
Can you share the screen again?
Yes. Okay. So why we are interested in the random purification? Because actually we proved that we can construct another purification channel that preserves the Gaussian nature of the mixed state. So basically, it's also true that if the initial state is Gaussian, you can construct Gaussian random purifications. So purifications of Gaussian states are not always Gaussian, but actually we can construct a random purification channel that maps Gaussian mixed states into Gaussian purifications. And we do this in the passive states. And okay, now this allows us to construct a non-Gaussian protocol to learn passive Gaussian states with this central complexity. This is because, okay, the random purification channel is not a Gaussian channel because it maps Gaussian states into convex combinations of Gaussian states. Convex combinations of Gaussian states are not Gaussian. And okay, so how to come up with a tomography algorithm? Basically, you add your raw tensor n copies of your unknown states. You apply the random purification channel. So now you have n copies of a fixed purification. You don't know which purification it is because it's random, but it's fixed across all the n copies. And then now you run pure state tomography on the states. And we know that pure state tomography, it's n squared, the central complexity. Since the purification has just a number of modes that is 2 times the one of the mixed states, we have that the tomography of mixed states is still n squared. It's like 4 n squared, still n squared. So this is why we can have the tomography of mixed states as basically the same central complexity of tomography of pure Gaussian states. And okay, this is not Gaussian, it's not a Gaussian channel. So this is a Gaussian scheme, a non-Gaussian scheme that can learn Gaussian states more efficiently than any Gaussian algorithm. Okay, so I think that I have to conclude soon. I think how many minutes? Okay. Okay, so just briefly go through the other results. So in conclusion, we have seen that, okay, so basically, before concluding tomography of Gaussian states, let me say that there are still open questions that in this on this problem. And for example, like questions about also the general case of tomography of mixed states under general measurements. We have these results just for passive Gaussian states, or also under other setting. For example, if adaptivity is like fixed Gaussian measurements from the beginning can be helpful or not. I mean, are still some open questions in this problem. So okay, now we see that tomography of Gaussian states is efficient. So now another problem is how to understand whether your unknown state is Gaussian or far to be Gaussian. So what is the sample complexity of testing whether an unknown state is epsilon close to be Gaussian or let's say 2 epsilon far from being from the set of Gaussian states. And we show that if for testing pure Gaussian states, these can be done efficiently in the number of modes, so polynomial sample complexity. But testing whether an unknown state is Gaussian, is a mixed Gaussian state or not, this has an exponential sample complexity. So there is a separation between pure Gaussian state testing and mixed Gaussian state testing. Okay, then another natural question is that we know that learning Gaussian states is efficient. What about processes? Is Gaussian unitaries efficiently to learn? And okay, Gaussian unitaries are basically the unitary analog of Gaussian states. Gaussian states were deep states of quadratic environments. Gaussian unitaries are just like unitary evolution of quadratic environments. And we show that tomography of Gaussian unitaries is efficient, meaning that the query complexity, the minimum number of queries of your unknown Gaussian unitary, in order to learn the unitary up to precision epsilon in so-called energy constraint diagonal norm, is polynomial in the number of modes. Here the guarantees are with respect to the energy constraint diagonal norm because for example, if you take two beam splitters with arbitrarily close transmissivity, but different, the diagonal distance is always maximal because you can put infinitely energy coherent states to distinguish them with probability 1. So, but this is not physical, it's just an artifact of the fact that we are inputting infinite energy into the channel. And so that's why we are using the energy constraint diagonal norm.
Sorry, so energy constraint diagonal norm means you constrain the energy of the input of the data channel you're applying.
Yes, yeah, the diagonal norm, the diagonal distance between two channels is defined as basically the supremum over all the input states. And of the trace distance between the output of the channels, so we also coupled with a zero. Energy constraint diagonal norm means basically that you constrain the supremum over all the states that satisfies an energy constraint. And then things now become well defined. And if you have, for example, the two beam splitters with approximately the same transmissivity but different transmissivity, these are close to each other in energy constraint diagonal norm, but they are maximal far apart in diagonal norm. Okay. So now, okay, we saw that when we have the Gaussian assumptions, things can be made efficient. And so it's natural to ask what is the trade-off between efficiency in learning and non-Gaussianity in the system. One can study this problem, and by using the so-called family of T-dot Gaussian states. T-dot Gaussian states are states that are prepared by applying to the vacuum Gaussian unitaries interleaved with non-Gaussian single mode unitaries. So for t equals 0, one obtains the set of Gaussian states, and as t increases, these encompass the full set of states. And by studying the sample complexity as a function of t, one can study how the sample complexity increases with the non-Gaussianity in the system, and how the efficiency in tomography increases with non-Gaussianity in the system. And okay, I'll skip these details. And basically, we show that it scales exponentially in the doping t. So if the doping is a constant, basically, tomography T-dot Gaussian state is efficient. Otherwise, it's not. And these parallels previous results in the Clifford setting and the fermionic setting. And there are also new. Okay, this was an example of tomography of non-Gaussian states. There are also recent papers on also the relevant classes of tomography of the structure of the relevant classes of non-Gaussian states, like boson sampling states. And okay, so in order to quantify the non-Gaussianity, before I told you that we quantify this non-Gaussianity by this parameter T of doping. And actually, from this parameter T, we can actually make this concept rigorous to define a measure of non-Gaussianity, so-called non-Gaussianity monotone. And this is defined, this is what we call the symplectic rank. Okay, I'll just go to the definition of symplectic rank and then stick to the conclusion. The symplectic rank of a non-Gaussian state is defined by taking the covariance matrix, write it in Williamson form, and the symplectic eigenvalues are always larger or equal to 1. And actually, it's very simple to show that they are all equal to 1 if and only if the initial state is a pure Gaussian state. And so psi is Gaussian if and only if all the symplectic eigenvalues are equal to 1. From this, one can define the symplectic rank, that is the number of symplectic eigenvalues strictly larger than 1. And okay, in our paper, we show that this is, okay, let's go to the conclusion. We basically show that symplectic rank cannot increase under post-selected Gaussian operations. So Gaussian operations also with the possibility of post-selecting on the outcome of the Gaussian operations and adaptively perform other Gaussian operations. And okay, just go to the conclusion. So, okay, this monotonicity of the symplectic rank allows you to find the no-go results in conversion of states via Gaussian operations. For example, it directly implies that any Fock state with n larger than 1, larger or equal to 1, can never be converted into a tensor product of, let's say, 1 Fock state tensor 1 Fock state, the tensor 1. So there are like no-go results that one can use, one can show via the symplectic rank, like irreversibility of the resonance theory of non-Gaussianity in the exact setting scenario. And okay, so let me skip to the conclusion. Okay, the last slides, it is like technical tools that can be useful also outside the specific problem of learning theory. And they can be used like also in other problems regarding continuous variable systems. That are these kind of inequalities that we use in all these papers to find sample complexity results. So in all these papers, when you have a trace distance guarantees, you always need to revert convert the error from the guarantees with the covariance matrix to the trace distance. So and deriving this kind of inequalities is technically difficult. And they can be useful also in other problems. We have like upper bounds of the trace distance, lower bounds for Gaussian states, and also lower bound for non-Gaussian states. And also another question that one can ask is that how the trace distance is related to the total variational distance between the beginner functions. And in principle, there is no direct relation, but operationally. But actually, one can show that the trace distance is equivalent to the total variational distance between the beginner, with can be always lower bounded by it, and upper bounded with a factor that scales with the number of modes. And actually, this square root of n can be removed for when you have the promise that the states are Gaussian, pure Gaussian states. Here, okay, the promise that the states are Gaussian. And okay, In conclusion, we provided an investigation of quantum Lerner theory with continuous variable systems, focusing on the problem of energy constrained states, obtaining the so-called like what we call extreme efficiency of tomography of continuous variable systems due to this scaling with epsilon. Then we show that tomography of Gaussian states and unitaries are efficient. And then we show that a trade-off between efficiency to tomography and non-Gaussianity. And we introduced a new model of non-Gaussianity, we call the symplectic rank. It's the number of symplectic values that are strictly larger than 1. And we showed bounds on the trace distance between two Gaussian states that can be useful also in other problems. Thank you for the attention.
Thank you, Francesco. Thanks for questions.
Ask you a question. Can you back one slide? Can you say, no, just this, yeah, this one, about the doping stuff?
Yes.
Can you say, I mean, there is an intuition how you deal with the fact that you get a non-Gaussian operation? Like, how do you deal with the doping of Gaussian states, and how do you control them to the bounds? I'm pretty much asking if there is any intuition as to how that works.
Okay, what is the algorithm that achieves that?
Yeah.
Okay, so the intuition is that basically T-dot Gaussian state, it can be shown that one can write it in this form here. So basically, there exists for any T-dot Gaussian states. So there exists a non-Gaussian unit that acts on two T-modes, and another Gaussian matrix that such that the T-dot Gaussian state can be written in this form. So basically, the non-Gaussianity of a T-dot Gaussian state can be compressed by applying a suitable Gaussian metric onto just two T-modes. So the intuition is that you call many copies of your unknown T-dot Gaussian state. You learn the covariance matrix. By writing the Williamson decomposition, you can kind of understand what is this Gaussian metric. And then you call other copies and basically you revert back these Gaussian matrix so that okay, I didn't show the slides. So basically, you apply the inverse of this Gaussian matrix. So now you obtain just a state that lives on two T-modes, and then you do full state tomography on the T-modes. And this
So, you say that the full circuit before is equal to this one, or every layer is. So the full circuit this one becomes the other one.
Yes, the full circuit of this one. Yes, actually, it also at the level of units. At the level of units, here you would also know the passive Gaussian units, but when applied to the vacuum, the vacuum unchanged. Yes, it applies also to the level of units. One can construct the G and the U explicitly in terms of all these components.
And
So I mean,
algorithm is single copy, like the estimation you use.
the algorithm you can make it single copy.
And then you said you perform full stack tomography on the.
Yeah, so the algorithm is basically, okay, the first theoretical observation is that actually saying that you have a T-dot states, it's completely equivalent to say that you have a state that has this structure, so two T-modes, Gaussian, so basically a non-Gaussian state over two T-modes and then a Gaussian matrix. So the protocol is that you first learn the Gaussian unity, so that on the next copies you undo the Gaussian unity, and then you do full state tomography on the two T-modes. This is the idea, and actually this is the same idea that was used previously in the Clifford setting and the Fermi setting by studying T-dot stabilizer states, T-dot Fermionic Gaussian states. And the same idea works but the proofs is different. The proofs are all different between each other.
Okay. If there are no more questions, let's thank Francesco.
Ciao.
Oh,
Ma